Hello everyone, I am Seshavidya, working in R.M.K College of Engineering and Technology as an Associate Professor in the Department of EC. So today in this video I am going to explain Unit 2 Digital Electronics. So the title is Combinational Circuit Design. The main objective of this Unit 2 is to familiarize with the design of various combinational circuits using logic gates. So in the second unit, the first topic is design of half adder and full adder. So before going into this design of half adder and full adder, let me tell you what are the classification of logic circuits and what is combinational circuit design. So this is a classification of logic circuits. Logic circuits are broadly classified into two types, combinational circuits and sequential circuits. And sequential circuits further divided into two types, synchronous and asynchronous sequential circuits. Synchronous circuits are again classified into two types, Moore circuit and Mealy circuit. Asynchronous circuits are also classified into two types, fundamental mode and pulse mode. And next one is introduction to the combinational circuit. So as I told you, the digital system consists of two types of circuits, combinational circuits and sequential circuit. So first let us discuss what is combinational circuit and then what is sequential circuits. Combinational circuit. So it consists of logic gates. That is, this is the block diagram of combinational circuit. It has n inputs and m outputs. So this combinational circuit, it consists of inputs, m outputs and also logic gates. So both inputs as well as outputs which will have binary signals. That is, both input and output signals are of two possible states. One is logic 1, other one is logic 0. Next one is sequential logic circuit. So the sequential circuit, this is the block diagram of sequential logic circuit. So it consists of combinational circuit and with this memory elements. So that is, the memory elements are also connected with the combinational circuit in the feedback path. So, and one more thing is, what is the difference between this combinational circuit and sequential circuit is that, so in case of combinational circuit, there is no memory element at all. But in the case of sequential circuit, there is a memory element. And one more the difference is that, so this in sequential circuit, the output of this sequential circuit, it depends not only on the present value of the input, but it is also depends on the past state of the inputs. So this is the basic difference between combinational circuit and sequential circuit. So this is the difference between combination and sequential circuit. So the first point is, so in case of combinational circuit, the output variable at all times depends on the combination of input variables. But that is in the sequential logic circuit, as I told you, and that output variable, it depends not only on the present input, but it is also depends on the past inputs. And the second difference is that memory unit is not required in case of combinational circuit, but in the case of sequential circuit, there is a memory unit that is to store the past history of the input variables. And third difference between this combinational logic circuit and sequential circuit is that in case of combinational logic circuit, in speed is very fast, that is faster in speed. But in case of sequential circuit, it is slower than compared to the combinational circuit. In combinational circuit, it is easy to design, but in the sequential circuit, it is somewhat harder to design. And the best example for the combination logic circuit is parallel adder, and best example for the sequential logic circuit is adder. And next one is, we'll just design of combinational circuit. So this is the actual topic of this video. So any combinational circuits that can be designed by using this design procedure. Okay. So based on the problem statement, that is, first they will be giving that problem statement. So based upon that problem statement given, we can just identify input and output variables. And then we can just assign the letters, that is letter symbols for input as well as output variables. And the next step is, with the help of input and output variables, we can able to construct truth table. So what's the purpose of the truth table is just to give that input and output requirements or combinations. And then we can write the Boolean expressions for various output variables in terms of input variables. So that Boolean expressions say that we can just say in terms of equations, or it may be in terms of binary bits. And finally, simplified Boolean expression that can be obtained either by using that algebraic method or Karnaugh map. It is also called as K-map, or by using tabulation method. Finally, we can just draw the logic diagram by using logic gates. So this is the design procedure for design of combinational circuit. So any combinational circuit that can be designed by using this procedure. Consider design of half adder. So this half adder, as the name implies, adder, it is nothing but just to add binary bits. So half adder, it's nothing but It's in combinational circuit. Okay. The purpose of this off adder is to add two binary bits. Okay. And one more thing is this off adder, it has two inputs and that represents two bits that has to be added. And it has two outputs. One is sum, the other one is carry. So this is the block diagram of off adder. So as I told you, it has two inputs and two outputs. So the two input bits, that is two binary bits, are nothing but and then bits that has to be added. And the outputs are nothing but sum as well as carry. So next one is, the next step is, by considering this input and output variables for the different combinations, we can able to construct the truth table. So this truth table consists of input and output variables. So according to this off adder, the input variables are A and B and outputs are sum and carry. So inputs A, B and outputs are carry as well as sum. So since input variables, there are two input variables, so we'll have the 2 power n combinations of inputs. That is 2 power n, where n is nothing but number of input variables. So according to this off adder, the number of input variables are 2. So 2 power 2 is equal to 4. So we will have the 4 combinations of input combinations. So A, B are the inputs. So that 4 combinations are either it may be both 0 or it may be 0, 1 or it may be 1, 0 or it may be both can be 1. So these are the 4 possibilities of input variables. So based upon this input variable combination, we can able to write the output variables carry as well as sum. So here we are going to perform manual addition. So as for that binary addition, 0 plus 0, obviously sum is equal to 0. So there is no carry at all. So carry is also 0. And if you add 0 plus 1, then sum is equal to 1, carry is equal to 0. And then the third condition is 1 plus 0. So again it is sum is equal to 1, carry is equal to 0. And in binary addition, if you add 1 plus 1, then output is actually 1, 0, where 0 represents sum and 1 represents carry. So likewise, we can able to construct the truth table. So next to this step, by using that either algebraic method or K-map or tabulation method, we can able to simplify the Boolean expression. So here we are going to use the K-map. And before using that K-map, first we have to decide and what is the type of the K-map that has to be used. So it is based upon the number of input variables. Now according to this off adder, how many number of input variables? 2, that is A and B. So that we are going to use 2 variable K-map. So this is the 2 variable K-map for carry and similarly for sum. Okay. So first we are going to consider for carry. So what are the 2 input variables? A, B. So that A, B, here we can consider A, B. So here it is, since it is an A, so which will have either 0 or it may be 1. And other variable is B, again which will have either 0 or 1. So likewise we can just construct the 2 variable K-map. Now we are going to represent for carry. So look at this truth table. So here it is carry is equal to 1. So we have to see that column where that carry is equal to 1. Here this carry is equal to 1 for the combination 1, 1. So A is equal to 1, B is also 1. So that represents this square. So you can just represent it as 1. Okay. Now we can just group this squares since it has only one representation. So we can just consider it as a single group. So for this single group, we can just write the mean term. So what is that mean term is? So here it is left hand side, it is equal to 1. Please remember that. And if it is 0, then it is nothing but complement of the variable. If it is 1, then we can just take that variable as it is. Now according to this group, the left hand side is it is 1. So which corresponds to the variable A. So we can write it as A as it is. And at the topmost, again it is equal to 1, which corresponds to the variable B. So we can write it as carry is equal to A into B. That is A dot B. Similarly, we can just do it for sum. So what is that sum column here? So that sum is equal to 1 for the 2 condition. Here one condition, here also one condition is there. So sum is equal to 1 for the combination 0, 1. So where is that 0? A is equal to 0, B is equal to 1. So this square. And then next one is, and sum is equal to 1 for the combination 1, 0. Where is it? 1, 0. So this representation. Now we can just group. So diagonally we can't group this once. So there isn't rule for K-map. So what can we do is we can just consider this as a single group and this as another group. So this K-map, it consists of 2 groups. Now we are going to write the mean terms for group 1 as well as for group 2. So first I am considering this group. So what's what left hand side? It is equal to 1, which corresponds to the variable A. And what is the topmost in that column? First column, it is equal to 0. So as I told you, if it is 0, then it is complement of the variable. What is the corresponding variable? It is b. So since it is 0, so we can consider as b bar. So for this group, that mean term is a b bar. Similar way for the second group. So this is the second group. For this one, the left hand side is 0, which is nothing but complement of the variable. The variable which is corresponds to the 0 is nothing but a. So it is a bar. And what is the topmost variable? That is bit. It is equal to 1, which corresponds to variable b. So we can write it as a bar b. So for the second group, the mean term is a bar b. And we have to write it in terms of sum of product term. So we can write it as a b bar. So this is the mean term from the group 1 and plus, and a bar b is nothing but mean term from the second group. So this a b bar plus a bar b, which is also is equal to a XR b. So that we can write it as a XR b. Okay, so this is a simplified expression from the K-map. Now we can just draw the logic diagram based upon the Boolean expression. So a sum is equal to a XR b, so that we can use that XR gate straight away. So inputs are a, b. So therefore output is equal to, that is sum is equal to a XR b. And similar way, what is carry? It is a dot b. So a dot b is nothing but it's a multiplication. So that is AND operation. So we can just use that AND gate. So inputs are again a and b. So therefore carry c is equal to a dot b. So this is the final logic diagram of the half adder. That way we can just design full adder. So what is the differences in case of full adder? Again, it consists of combinational circuits and combinational circuit. So it will perform the addition. The only difference is that which will sum the 3 input bits. That is, it consists of 3 inputs and 2 outputs. So the first two input variables are nothing but the significant bits. That has to be added. The third input bit that represents the carry from the previous lower significant position. So that's nothing but carry in. So this is the block diagram of full adder. So as I told you, there are 2 input variables A, B. So these are the 2 bits that has to be added, and one more input is from the previous lower significant position. So that we are naming it as C in, that is carry in. So again, which will perform the addition. So therefore outputs are again 2 outputs. One is sum, the other one is carry. Since already we are mentioning it as carry in, so output we are just mentioning it as carry out. So now based upon this input variables and output variables, we can able to construct the truth table. So inputs, outputs. Now according to this, how many number of inputs? A, B, C in. And outputs are sum and carry. So as I told you, we can just write the truth table input combinations that is based upon the formula 2 per n, where n is nothing but number of input variables. According to this one, how many number of input variables? 3. So 2 per 3 is nothing but 8, which means which will have the 8 combinations of input variables, that is input bits. So which will start from 0 to 7. So we can write a 3-bit input, that is a 3-bit binary from 0 to 7. So 000, 001, 010, likewise up to 7. That is starting from 0 to 7. Okay. So now we can just perform, that is manual addition. So sum, we are going to find the sum and carry. So first we are going to add the first 2 bits. 0 plus 0, 0. Again 0 plus the previous carry is 0 initially. So 0 plus 0, 0. So both sum as well as carry is equal to 0. Second case, 0 plus 0, 0. 0 plus 1 is 1. So sum is equal to 1, carry is equal to 0. Third case, 0 plus 1, 1. 1 plus 0, again it is 1. So sum is equal to 1, carry is equal to 0. So this condition is very, very important. 0 plus 1 is 1. Again 1 plus 1, as I told you, the output is 1, 0. Where 0 is nothing but sum and carry is equal to 1. Next one is 1 plus 0, 1. And 1 plus 0, again 1. So sum is equal to 1, carry is equal to 0. Next case, 1 plus 0, 1. Again 1 plus 1 is, it's 1, 0. Where 0 is nothing but sum and 1 is nothing but carry. Similar way in this case also, 1 plus 1, it's nothing but 1, 0. So which means sum is 0, carry is 1. So the last condition is very, very important. So if you add 3 1s together, so what will happen is 1 plus 1, actually it is 1, 0. Again if it is one more 1 is added to the LSB bit, then it becomes 1, 1. So which means sum is equal to 1, carry is also is equal to 1. So likewise, we can able to construct the truth table for the full adder. Now we got the truth table. Now we can just simplify this truth table using K-map. So how many number of input variables here? There are 3 input variables. So we have to use 3 K-map. Okay. So this is a 3 variable K-map for carry as well as for the sum. So what is the 3 variable? A, B, C. So in that left hand side, it has only one variable. So which will have the 2 combinations 0, 1. But in the topmost variable B, C. How many number of variables? 2 variables. So which will have the 4 combinations 0, 0, 0, 1, 1, 1, 1, 0. Now we can just represent that carry. So we can just consider that carry column. So wherever that carry is equal to 1, the corresponding combinations that can be represented in a K-map as 1. And then we can just group that once, and then we can just able to find the simplified expression. So for example, carry is equal to 1 for the combination 0, 1, 1. Where is that 0, 1, 1? 0, 1, 1. So here we can just represent as 1. Again, carry is equal to 1 for the combination 1, 0, 1. Where is that 1, 0, 1? 1, 0, 1. So this square that can be represented as 1. Again, that carry is equal to 1 for the combination 1, 1, 0. So 1, 1, 0. So this one. And finally, carry is equal to 1 for the combination all ones. So 1, 1, 1, 1. So this one. Now we can group this ones. So this 2 ones as a group, this 2 ones as a group, and this 2 ones as a group. So it has 3 groups now. For all 3 groups, we can just write the min terms. So for this group, that is for this group, what is that? Left hand side is 0, 1. So it get cancelled. So which will have only that B, C. So this is here. And similar way for this group. For this group, left hand side, what is that variable is nothing but 1. So we can write that A as it is. And here the topmost is, it covers this 2. Okay. So here what will happen is, first variable get cancelled. Why? Because here it is 0, here it is 1, it get cancelled. So which will have only C. So what's that left hand side? A, C. So this is here. And next one is this group. So what's the left hand side again? It is equal to 1. So that means A. So now we have to consider this 2 columns. So what will happen? The second variable that get cancelled. So which will have only that first variable. So what's that first variable according to this one? It's B. So left hand side is A and topmost variable is B. So AB. So likewise, we can able to find the min terms from the each group. Finally, we can just add it together. Similarly, we can just do it for sum also. So this is one method of representation for full adder. And for this simplified Boolean expression, we can draw the logic diagram as it is. So sum is equal to, there are 4 min terms. So that 4 min terms are added together. So for that 4 min terms, we'll be using 4 AND gates here. 1, 2, 3, 4. And finally, all 4 min terms are added together. So we'll be using OR gate here. And next one is carry. It consists of 3 min terms. So we'll be using 3 AND gates here. And finally, these 3 min terms are added together. So finally, we'll be using OR gate here. So likewise, we can able to represent the full adder. And there is a method to represent this full adder by using 2 off adder circuit. So for that, what you have to do is, we have to simplify that expression in such a way that, so that full adder that can be implemented using 2 off adder circuit with 1 OR gate. So this is some, for example, we are just considering that some expression as it is. And if you just look into this equation and see that first term and last term. So from the first and last term, shall we take C in as common? Yes, exactly. We can take C in as common. Similarly, from the second and the third term, shall we take C in dash as common? So here also we can just take C in dash. So likewise, we can just able to simplify this sum expression in such a way that C in XOR A XOR B. So this is a simplified Boolean expression for sum, so as to implement by using 2 off adder circuit. So we can consider carry expression also. So carry out the expression is AB plus AC in plus BC in. So here will be just for simplification purpose, we'll be considering that that is A plus A bar. It is nothing but actually 1. So for simplicity, that is to just derive that expression in such a way that to get that 2 off adder circuit. So we'll be just using that simplification process here. So just we'll be multiplying with A plus A bar. Anyway, it is equal to 1. There is no change of meaning, but A plus A bar. So just multiplying this A plus A bar, and again by applying C in plus 1 is equal to C in. And finally, we'll be getting that the final expression for C out as AB plus C in A XOR B. So this is the final expression, that is a simplified expression for C out. Now we can just draw the diagram, that is we can just implement the full adder by using two off adder circuit and one OR gate. Okay, so there are three inputs A, B, C and outputs are sum and carry out. Okay, you can just check with this sum and carry out expression with this diagram. So this is very important question, implementation of full adder with two off adder circuit and one OR gate. So